here we're going to see how we can use certain restrictions on manufacturing, on labor, to see what type of production will maximize profit. So here in this example, a clothing manufacturer has 60 yards of cloth. This clothing manufacturer, this question deals with shirts and vests. Shirts require 3 yards of cloth, and vests require 2 yards of cloth. So there's our first piece of information. Well, actually the 60 is our first piece. The next, we have shirts generate a profit of $5 each, vests $3 each. And the question is, how many of each should be sold to maximize the profits? And here we're going to see that a couple observations on lines will help us find the maximum profit for this system. So first, let's what should we do first? Let's define the variables first. Let's let X be the number of shirts sold, and let's let Y be the number of vests sold. Because now with this we can set up a profit equation. Maybe I should have written the profit sentence first. Actually, let's not do the profit first. Let's deal with the cloth first, since that's how I wrote the question. So if X is the number of shirts, and shirts require 3 yards of cloth, well, then 3 times X tells you how many yards of cloth are devoted to shirts. So 3 times X, shirts are 3 yards of cloth. X is the number of shirts, so if you have like 5 shirts, then you would need 15 yards of cloth. 15 is 3 times 5. So 3X is the amount of cloth devoted to shirts. Vests require 2. Vests are called Y. So shirts require 3 yards, vests require 2 yards, and we have 60 yards of cloth. So we have to use at most 60 yards of cloth. So the total cloth we used for these two products is 3X plus 2Y, and that must be less than or equal to 60, because maybe we'll use up all of the cloth. And now let's find a profit equation. Profit, shirts generate $5 per shirt, vests generate $3 per vest. So profit, which we'll call P, $5 per shirt, $3 per vest. So $5 per shirt, $3 per vest. Why does this, well, maybe I'll explain a little bit. Why does this work? Let's look at the units. What is it? It's $5 per shirt. And what's X? So it's times X shirts. So if you multiply this out, the shirt and the shirt cancel, and you're left with units of dollars. You're left with 5X dollars. So 5X is the dollars that you generate by selling X shirts, the profit from X shirts. And what about 3Y? Well, that's the same with vests. It's $3 per vest times Y vests. And now, all we're going to do is use a theorem. Actually, no, we're not going to use a theorem. I'm going to draw a picture and then use a theorem. So this inequality, let's graph this inequality. How can we graph this? Well, I'll tell you right now, this is a line. And the easiest way to graph this is actually to find the x-intercept and the y-intercept. So let's graph 3x plus 2y is less than or equal to 60. It's a line because it's just one x and one y. And the easiest way to graph this will be to find the x and y-intercept. How do you find an x and y-intercept? Well, what's the ordered pair? Let's do the x-intercept first. What's the ordered pair on an x-intercept? Well, it goes over x up 0. So an x-intercept will occur when y equals 0. So let's find that. I guess I can probably do it over here. X-intercept occurs where y equals 0. So 3x plus 2 times 0 equals 60. To graph an inequality, we'll first graph the equal sign and then interpret the inequality. So for the x-intercept, let y equal 0. So you get 3x equals 60. So x equals 20. So this point over here is 20, 0. What about this point up here? Well, this is a y-intercept. What does that look like? Well, you go over 0 and up some y value. So that can be found by letting x equal 0. So let's let x equal 0 in our line. Yeah, okay, I guess I'll hope that stays that time. Let's let x equal 0. So you get 3 times 0 plus 2y equals 60. 0 plus 2y equals 60. Y equals 30. So here we have the x and the y intercepts. So that's 0, 30. Well, once we have the two intercepts, we can draw the line. I mean, you could pick any 2 points on the line, but the intercepts are usually the easiest to find algebraically. So we have this line. Well, that's wonderful. How can we interpret that? Well, the inequality, since it's less than, we're going to assume x and y are going to be only positive numbers, or 0. So we're not going to deal with negative x and negative y. In other words, we're just going to restrict ourselves to the first quadrant and the axes. And now, this less than tells us not only do we want the line, but we want to consider that entire piece. Now, here we have this constraint on fabric. And the constraint on fabric is reflected by this graph. And there's a theorem in math called the corner point principle. That should be LE principle, not AL principle. The corner point principle. The corner point principle, oh, I forgot to define a word. What I almost got there, but I was half a sentence away. So this inequality defines this piece of the graph. This piece of the graph we call the feasible region. So the feasible region occurs where, well, any point within the feasible region can be satisfied by the given constraints that you have. So any point in here will satisfy all of these equations. And remember, we're going to assume the number of shirts and vests that we sell is positive. So that's called the feasible region. The border lines are included in the feasible region because it's an equal, less than or equal to. The corner point principle says the maximum profit always occurs at a corner point of the feasible region. What do we mean by a corner point? Well, the feasible region is going to look like the intersection of a bunch of lines, kind of. And right here, when any two lines intersect, it generates a corner. So up here we have a corner point. Down here we have a corner point. But we also have this other corner point over here that must be considered. So let's write that down. Here we have 3 corner points. here we have 3 corner points. And what are they? Well, we found them over there. We found 20, 0. We have 0, 30. But we also have the origin point, 0, 0. So here we have 3 corner points. And the corner point principle tells us that the maximum profit always occurs at one of the corners. So all we have to do now is look at the profit evaluated at those corner points. The profit was, I forget what it was, I just erased it and it was right in front of my eyes. 5x plus 3y. Well, all we have to do is evaluate that at these points. So let's, I don't know, let's make a chart, I guess. Point and profit. So let's start with 0, 0, because that's easy. Profit is 0. 20, 0. Well, when x equals 20, the profit is 100 plus 0. What about when at the point 0, 30? Well, 0 times 5 is 0. 30 times 3 is 90. 0 plus 90 is 90. The largest of these gives us the largest profit. So we can reach our conclusion. So the manufacturer, I'll just call it manu with a period, should make, what, 20 of X and 0 of Y. 20 shirts and 0 vests to maximize profit. Now, in this example, our feasible region was relatively uncomplicated, because once we found these 2 points, we were largely done. Now, right here, you'll notice this feasible region was generated by one line and the axes. Well, what if we had an example with more than one line? So here we have another example. A toy manufacturer has 60 units of plastic and 360 minutes of labor. A skateboard requires 5 units of plastic and 15 minutes of labor. A doll requires 2 units of plastic and 18 minutes of labor. Skateboards can be sold at a profit of $1. Dolls can be sold at a profit of 55 cents. Find the level of production that maximizes profit. Well, the first thing we notice here is in the first example we had one restriction. Here we have 2 restrictions. We have a plastic restriction and a labor restriction. So let's first interpret those restrictions using inequalities. Well, let's deal with plastic first. We have 60 units of plastic. We have 5 units of plastic per skateboard. We have 2 units of plastic per doll. Well, actually, let's first define variables. So let x be the number of skateboards. Let y be the number of dolls. Well, with the plastic restriction, we have what? 5 skateboards and 2 dolls, or 5 per skateboard and 2 per doll, must be less than or equal to 60, because all we have are 60 units of plastic. Well, what about the labor restriction? We have a second constraint. Each skateboard is 15 minutes of labor. Each doll is 18 minutes of labor. And our total labor must be less than or equal to 360 minutes. So we have 2 equations from all that information, so I can erase the first few parts of this example. And the only other thing we need is a profit equation. So let's write the profit equation now so we have it when we need it later on. So the profit says skateboards can be sold for a profit of $1, dolls for a profit of 55 cents. So our profit equation is 1 times x plus 55 hundredths times y, which of course is just x plus 55 hundredths of y. 55 hundredths is 11 twentieths. I'm just going to write that like, why is it 11 twentieths? Well, it's 11 twentieths from what? You move the decimal over, you put it over 100, then you reduce. What's another way you could reach that conclusion? 55 hundredths. Where have we seen 55 hundredths of a dollar, say? Well, a nickel is a 20th. 55 cents is 11 nickels. A nickel is a 20th of a dollar. Or you could use the other way. Or you could leave it as 55 cents as the decimal. So where were we? I'm just going to write these other restrictions as well. So we have our profit equation. I'm just going to rewrite these up toward the top of the board. So the next thing we'll do is find the feasibility region, or the feasible region. And we'll do that by graphing these two lines. And then we will put them on the same graph. So let's first graph them separately, and then we will combine them. So first we'll graph 5x plus 2y is less than or equal to 60. So we'll again do it by using the intercepts. So this one occurs, what is it? It's over x up 0. So y equals 0. 5x would then equal 60. X equals 12. So we have 12, 0. Up here, you go up, or sorry, you go over 0 up y. So x equals 0. And then you get 2y equals 60. Y equals 30. So this has ordered pair 0, 30. Now I'm going to erase these computations because they're going to get in the way of the graph. So we have this line, but the inequality would restrict us to that region. Well, let's do that with the other one. Same thing, except different numbers. So again, for the x-intercept, it goes over x up 0. Over x up 0, so we let y equal 0. So you get 15x equals 360. 360 divided by 15 is 18. So you get 18, 0. Why is it 18? Why is it 18? Yeah, good job. It is not 18. 15x equals 360. X equals 24. Now, why is it 24? And what did I do to check myself? I think the other one winds up being 18. No, maybe I just have 18 in my head from that. Yeah, okay. How do we get 24? Well, 15 goes into 150 10 times. 300 is 150 and 150. So 15 goes into 300 20 times, and you're left with 60. 15 plus 15 plus 15 plus 6. 15 times 4 is 60. So you get 300 plus 60, 20 plus 4. Or you could reduce a fraction, cancel out a 5 and a 3 or something. The other one up here, an x-intercept goes over 0 up y. So you let x equal 0. So you get 18, y equals 360. So then y equals 20, because 18 times 2 is 36. So we have 24, 0, and 0, 20. So both of these lines describe a feasible region. But that's only for their own constraint. This entire system uses both of those constraints. So let's put those lines on the same graph. And I'm going to do that over here. Let's put them all on the same graph. And now I'm going to be kind of close to scale. So first we'll go to 12, 0. Then we'll go over to 24, 0. And on the other axis, what do we have? We have 20, so 0, 20, and 0, 30. And all we have to do now is find the feasibility region by drawing these lines. And I'm only going to draw them in the first quadrant. The feasibility region will be where both of them are satisfied. So the feasibility region here is in that piece. We don't need these over here anymore, since we have the feasibility region, or feasible region, not feasibility region, feasible region. Feasibility region actually doesn't make sense. So right here is the feasible region. So all we need to do now is apply the corner point principle, which says that the maximum profit will occur at a corner point. Well, let's label our corner points. Here's one, 0, 20. Here's one, 12, 0. Notice we don't consider that. That's not in the feasible region. Just this shaded piece and their borders. Oh, here's a corner right here. 0, 0. But look what we have up here. We have another corner point. How do we find that corner point? How can we find that corner point? Well, let's look at where that corner point occurs. That corner point occurs where these two lines intersect. So right now, the goal will be to find an ordered pair for this corner point. And that occurs where the two lines intersect. So I need the equations for the lines. We don't need the inequalities for this part. So to find last corner point. To find last corner point, what are the line equations? We have 5x plus 2y equals 60. And we have 15x plus 18y equals 360. We have two equations, two variables. We can solve them. Now, there are a couple ways you could solve these. One of them is to go into this first example, solve it for our equation, solve it for y, substitute here, solve for x, resubstitute back for y. I find that a little difficult. Not difficult mathematically, but very easy to make a mistake that is easy to make. Another way to do it is by playing with these equations. And what I mean by that is, let's force the coefficients here to be the same. What can we do to make those the same? Well, can we do something to this first one to make it look like a 15? Well, yes, we can. If we multiply the first equation by 3, what happens? Well, we get 15x plus 6y equals 180. That's from multiplying the first equation by 3. So maybe I'll write that over here. Multiply first equation by, in this case, we multiplied by 3 so that the coefficients on x were the same. We'll leave the second equation alone. So we wanted the coefficient on x to be the same. Because now what we can do is subtract this entire equation. And if we do that, what happens? Well, 15, we've set ourselves up so that all we have to do is pay attention to coefficients. 15x minus 15x is 0. 6y minus 18y, negative 12y. 180 minus 360 is negative 180. So we have 0 minus 12y equals 180. So that's the same as negative 12y equals negative 180. That's the same as y equals 15. So this first thing, multiplying by 3, allowed us to get rid of all x's in our equation. We got rid of all the x's. We were left with just a y. So now, this ordered pair has y value 15. Well, how can we find the x value? Well, all we have to do is substitute this y equals 15 into one of these two equations. So I'll say substitute y equals 15 in that equation. You get 5x plus 30 equals 60. Solve that for x, you get 5x equals 30. So subtract 30 from both sides, divide by 5, and you get x equals 6. So when you have two lines and you want their intersection, a process like this will help you find it, or could help you find it. Well, will help you find it. So write your two equations in order like this, and then multiply one of them by something that allows you to do a subtraction like that. Because you want the coefficients to be the same, because they produce this 0. Well, all that work was to find this last corner point. So now what we need to do is find the actual profit. With something like this, with this 5500ths, I would allow a calculator with a number like 5500ths. The examples I would come up with are usually like numbers like 2 and 3 and 4. So maybe not with those. But here, I would allow a calculator with a number like that. This example is from the book. So now we apply the corner point principle. The corner point principle says profit is maximized at one of these quarter points in the feasible region. So we have the origin point, we have 0, 20, we have 12, 0, and we have this last point, 6, 15. And for profit, we use the profit equation. So 0 plus 0 is 0. 0 and y equals 20. Well, when you write 55 cents as 11/20, y equals 20. We'll just cancel out that 20. And you get 0 plus 11, which equals 11. For 12, 0, what do you get? You get 12 plus 0, which is 12. Now what about 6/15? 6/15, you get 6 plus 11/20 times 15, which we can write like that. 6 plus 11/20 times 15. What does that equal? That equals 6 plus 15/20 is 3/4. So 33/4. 15 over 20 is 3/4. 3 times 11, 33. So what is this profit? That's 8 1/4. So I'm just going to say 14 1/4. Mixed numbers are nice for this because you generally think of dollars as being whole dollars. When you have $50 in your pocket, you don't walk around saying, "Oh, I have 5,000, not 5,000 dimes. What is it, 50 dimes in a?" No, it's 50 dimes in a roll. A roll is 5. It's 10 dimes. When you walk around with $50 in your pocket, you don't say, "I have 500 dimes." You would say, "I have $50." Or if you had 501 dimes, you would say, "I have $50 and a tenth of a dollar," or 50 and 10 cents. But where were we? We were trying to maximize the profit. So here we have these numbers: 0, 11, 12, and 14 1/4. So they should make 6 of X, 6 skateboards, and 15 dolls to maximize profit, because 14 1/4 is the largest of those numbers. Now, one last observation we'll make about these examples. The information could be written in a chart that might be helpful for setting up the equations. So with this example, and with the initial phrasing of the question, I'm not going to rewrite the question because maybe you have it in your notes. If not, just remember the numbers, I guess. But the initial information can immediately be turned into a chart. So let's see how that would work. So let's say information can be organized in a chart. And what kind of chart? Well, let's make it look like this. Skateboards, we'll say, are here, and we'll call them X. Dolls, we'll say, are here, and we'll call them Y. And let's just list our constraints and our profit. So plastic, we'll put up here. Not plastic, labor, we'll put here. And profit, we'll put here. And plastic, we will just note up here that we have 60 units of plastic. We'll note we have 360 units of labor. And profit we'll just call P. So we set up the information with the constraints and the profit and the information like this. And skateboards needed 5 units of plastic. Dolls needed 2 units of plastic. Skateboards needed 15 units of labor. Dolls needed 18 units of labor. This one had a profit of $1. This one had a profit of 55 cents. And with this, you can set up your inequalities like this. 5 times X plus 2 times Y is less than or equal to 60. Similarly here, 15 times X plus 18 times Y is less than or equal to 360. And I would normally write this under. I guess I'll write it under like this. With profit, profit is just 1 times X plus 55 hundredths times Y. So that's X plus 55 hundredths Y. So you could use a chart to set yourself up. I didn't. But you can use that. It is helpful for organizing. It's helpful for making sure you put the right numbers in the right spots. So another example that is worth trying is on pages 139, 140 of the textbook. I think it's worth looking at. It's similar to this one, so I'm not going to go over it here. So see how that goes. The only thing I will comment here, the x-intercept point in their feasible region, they write as 66.67 or something. Write that as 66 2/3 or 200 thirds. It might make the computations easier.